We are being recorded. And so let's talk about, and this is actually a topic that I, in some classes, spend not a whole class period on, but spend more than a little bit of time, is nonlinear relationships, and this has been somewhat of a consistent conversation and that's why I told you just before spring break that I'm going to be sure to put a period on this conversation. But when we were doing this analysis, this is when we first started doing multiple regression, and the dependent variable that we're looking at is the religious service attendance. And then we had a half a dozen different independent variables. One of those independent variables was income. And so we theorized, is income positively related? As income goes up, do people attend religious church service more? Or is it inversely related? Or as William said for sure, and I don't remember who else also, thank you, it might be a nonlinear relationship. And I said, well, we can test that. And we started testing that. In one class period, and we ran into some problems with multicollinarity, and I wasn't quite able to get it fixed in front of everybody that day. And so I just want to go back and revisit that and show you how we would be able to do that assessment, and it would just be something that you don't have to have for other work we're going to do in this class, but certainly is a useful tool to have when you start thinking about doing data analysis on your own, because I really think there are a lot of undiscovered nonlinear relationships that are either disguised as being non-significant relationships or linear relationships that are attenuated or shown to have smaller effect sizes than maybe they actually do. Because if we have a nonlinear relationship and we try to draw a straight line through that, we're going to capture some of the linear part of that nonlinear relationship, and so the relationship won't be zero, but we're missing a lot of it because we're not modeling. We're modeling it as a straight line instead of as a nonlinear line. And so to have this as a way for you to look at data as you continue to do research, I think it can be a valuable resource. And so we're just going to redo the analysis that we originally did. By the way, how many people have where their SPSS starts up really slow on an Apple computer? I know what it is. You have to edit your host file, and so I can show you how to do that. I did a Google search, and it's called hosts. It's a file that you want to be really careful about editing. We just have to add a little bit of text to it, because when SPSS starts up, it's doing some kind of network search, and it doesn't have quite all of the information it needs to do that. And if you give it just a little bit more information, now my SPSS starts up as fast as it did on my old PC. And so I can show you how to do that, and it's really pretty straightforward. And we'll do that maybe after the break. So if we redo the analysis, we are doing linear regression. Our dependent variable is how often they attend religious service, and our independent variables is do they pray, strength of affiliation, belief in life after death, education, age, and income. And I'm going to stick all of those in there. I'm going to ask for some statistics, and I want descriptive statistics, and we'll get collinarity diagnostics. What else do we ask for here?
Is it case one?
We can do this, sure. What's that? What else do we have?
You can do R squared change if you take out one of the variables.
We can add that. We won't need it yet because everything is just in a single block, but we'll have it for later.
Yesterday we learned from every homework.
Okay, and so here's our analysis, and this is just it should be straight away pretty close to what we had earlier, where we find that the variable of interest is income. As income increases, religious service attendance also increases. And in fact, if we look at the standardized betas, well, it's moderately sized. Any problems with collinarity here?
No,
Why?
because none of the conditions are 30.
Yep, none of the condition indexes are above what?
Is it 30 or 32? 30?
I think 30, right? Was it 30? It seems. How about what would we look for with tolerance?
Less than 0.1?
Yeah, less than 0.1. Everything's fine here. And so if we want to model a nonlinear relationship, we have to simply add in that nonlinear feature into our model. And so if we think age might be related in some kind of a inverted U or U-shaped relationship, that would be a quadratic relationship. So we would square, we'd have to add the square of income. It could be a cubed relationship, would be sort of a sideways S. We might add that in just to see if it matters. We're not going to do it here, but that could be another thing that you might add. But we would almost never go beyond, we wouldn't add in a fourth degree polynomial or fifth. At some point, you could almost model your data exactly to some relationship if you add in a polynomial that's high enough. And so usually with the social sciences and everything that I've read, we do quadratic and maybe a cubed. Thank you. Relationship. And if we don't find any nonlinear associations there, we're probably best off just stopping. And so what we did last time, and this is what I'll do again this time, is we can compute a new variable, and so this is going to be our income variable that I'm just going to take the square of. And in SPSS, I think it's this, right? That should do it. That should do it, right? I think in some programs we use caret, right? I don't think SPSS likes that. I think we do 2 asterisks and then what power we want it raised to. And so now we should have a new variable. And if we just redo our analyses, adding in that new variable, I'm going to put it in, see we have block 1 of 1 here. I'm going to put it in a second block of variables. You don't have to do it this way, but this is probably best practice. We'll put the square of income in that block of variables. And I think our statistics are still all good. And we're going to run the analyses. And if we look at our results, we can see that, well, first of all, the second block of variables didn't make a significant contribution to the overall R squared because this F test not significant. The original block of variables did, because that's the same variables as we had originally. And remember, the second block is only the square of income. And so if this were to be significant, that would mean we'd have a nonlinear relationship. But the problem that I think we have is that there's a high correlation between the square of income and actual income. And so if we look at our tolerance, we can see our tolerance for the square of income is 0.04, which is quite a bit below that threshold that we said 0.1 or below would be cause for concern. And so we can also look at our other collinarity diagnostics, and we see that the highest condition index is 81, far above the 30, and we can see that income and the square of income is what's causing the problem. And so the traditional fix for that is, and there's a classic book, Aiken, and I can get the reference. Aiken, and I forget who Aiken's co-author was, but they have a book on regression and really testing for nonlinear relationships, testing for moderating relationships as well. And they indicate that a best practice would be to center the independent variable, and then create the nonlinear term out of that centered variable. And so I'll show you how we can do that, and I'll show you how it should reduce that level of multicollinarity, and we'll see how it goes. And so the mean for income, help me remember this, the mean for income is 10.95. And so to center a variable, I'm just going to take, and this is our listwise mean, which is what we want to have, because if I did the mean for all of the data, it might be different than the 10.95 because I've listwise deleted out some people. So the 10.95 is the mean that we want, and I'm going to do transform and compute, and I'm going to do, this is just going to be called center income, and I'm going to just do income minus 10.95. And so now the new mean will be 0, right? Because I take every score minus the mean. The new mean will be 0, and values below the mean will be negative. Values above the mean will be positive, right? And so I'm going to run this analysis. And so I've created that centered variable. And now what I'm going to do is do another transformation and create the nonlinear term out of center income, and I'm going to do this. And so last step then would be, let's redo our analysis. We can get rid of the square income. We're going to go to the previous box, and we're going to get rid of income. And I'm going to use the two terms that I just created. One is our centered income, which again, all we changed is where the mean was, right? We didn't change anything else. We just changed the mean. So we're not. It's just a transformation that is pretty straightforward. Then the second block, I'm going to put the centered income square and add that. Run everything again. And in this case, if we look at our R squared change for the second block is not significant, so there's no nonlinear relationship there. But more importantly, for our purposes, because I didn't have much confidence in the analysis that we did, because the collinarity diagnostics showed it was 0.04, showed it to be a problem. But here, the collinarity diagnostics, the tolerance goes up from 0.04 to 0.21. And then if we look down here at our other collinarity diagnostics, the highest condition index is 17, and we talk about 30 as being a reasonable place. And so the answer to the question is I'm confident that there's no quadratic nonlinear relationship between income and how often somebody goes to attends religious service, at least with this data. There might be a cubic. I'm not testing that, or there might be some other I wouldn't say there's no nonlinear relationship, but it's not a U or an inverted U relationship. So the key here was to get around or to fix the problems with the high collinarity. We centered that independent variable, and the high collinarity was caused by we had income and we had income square, right? And those two things are going to be highly correlated, right? If you take somebody's income and then square their income and correlate the two, they're going to be highly correlated. And so that caused problems with the estimation as identified by the or the low tolerance level. And the standard way to fix that is to center your variable and then create the nonlinear term from the centered variable. And in this case, it worked reasonably well. In some cases, it works a little bit better. In other cases, it doesn't work quite as well. But in this case, I have confidence that there is a relationship between income and religious service attendance, and it seems to be just a linear. As income goes up, people tend to attend religious service more frequently. So questions, confusion? Again, more just FYI or something that you can put in the back of your mind as a potential analysis you could do if you have reason to believe that other work that you're doing has things that are related in some way that's not just linear. So, good enough? And so I want to sort of pick up. There's just a few slides. There's just a few slides from. By the way, other questions from homework 4. You just submitted it a few minutes ago. I had a few meetings. I met with a few people this week that all had good questions. William?
I just had one with, because my scatter plot and the parallel analysis was both saying I should have 4 categories.
Discrete plot?
Or discrete,
Yep.
discrete plot, right?
Yep.
So, but then I, every time I tried to do 4, it just had tons of, one variable was on its own, and then everything else was just
What was the eigenvalue for the fourth component? Was it greater than 1, I assume?
Yes. Yes, it was 1 point. Actually, it was 4.57.
For the fourth
I'm
component?
sorry. 1.14.
1.14. And then what was the eigenvalue for the fifth?
0.69.
And then the third?
1.823.
Yeah, and so the parallel analysis said you needed 4. But it extracted 4 for you too, because just using eigenvalues greater than 1?
Yes, it extracted 4 for me. But then the fourth one, like I said, was just one item.
Oh.
And then all the other items were cross-loaded, and they were cross-loaded heavier on the other 3. So it just had one item in the fourth one. Which is
So you the fix, you deleted that one item?
No, actually, I changed it to have 3.
Okay, and kept that one item?
Yes, and kept that one item and
Yep.
deleted, because it was like at 0.8, so I deleted some of the other ones that were at 0.4, and then it ended up fitting together that way, but only on 3 factors, not on 4.
Right.
So.
And there might have been other ways to get to a slightly different solution, but that's why it's called exploratory analysis. And another way to do, so what if you would have done 3 and just deleted that one item that seemed to be causing problems? Would have I gotten to sort of the same place that you did or not? Because
Possibly, but probably not. But maybe not, because the other ones that were.
You just kept that one item, right? The one that loaded by itself.
And it ended up loading on another.
Oh, it did.
Once but the other ones, they ended up being the problematic ones. They were cross-loading. So.
And so you eventually deleted them out, and this is what you were using the apprehension data.
I combined 2 of the scales, the apprehension and communication competence, because everybody says that they're the same scale, or some people say they're the same scale. So
Okay.
I combined them to see if they actually were, and actually ended up loading.
Yeah. I think the way that you did it is perfectly reasonable. There might have been other ways to do it. Again, it's exploratory, and there's not hard fast. You do it this way and not that way. And so it seems that the choices that you made are defendable, and you'd be able to probably write it up in a way that would be defensible. So
I just was kind of getting locked, I guess, on the fact that it said we had to, like, 4 in the parallel analysis, that we had to have 4, maybe.
But you got rid of
But you're saying that 3 is okay, like it's like just not more than 4. So like. Okay,
that's why if I would have, because the one item loaded all by itself. See, I would have just thrown that one out and done 3 then. For some reason, that just seems like the route that I would have gone, instead of keeping it and doing 3 is what you did, right?
Yes, I kept it in force 3 and then saw how it ended up.
Right. What would have happened if you would have thrown it out and forced it to do 3?
I don't know.
Yeah.
I can check.
You don't have to. But I think, to answer your question, I think it's not as long as it's less than, it's okay. I think the parallel analysis tells you, or eigenvalues greater than 1, or the scree plot tells you the number of, components that should be extracted from your data. And that would be the number that you'd want to extract. But if you delete the one component that had only the one item on it, then it seems reasonable to go from 4 to 3. If you keep that one item and force it to do 3, eventually it worked out for you, but it just probably isn't the way that I would have gone. But again, it's not. There's nothing wrong with what you did. It seems to me anyway.
I think too, what I was looking at was the variance explained. It only went up from 72 to 75, from 3 to 4. So that's why I was like, well, it's only 3%. Like, so let's just leave it in and force 3 and see what happens.
Yeah, and then you had to get rid of a bunch of other items.
2 other ones.
Oh, just 2 other items. Yeah. So I think one just has to be flexible as you're working through the process, and if you delete full components, you have to adjust. You have to make adjustments along the way. I assume that if you did a parallel analysis with your final analysis, that all of the components would be um, above the 95th percentile from the parallel analysis, right?
Yes.
Yeah. So that's probably what matters the most. Good. Other challenges with the homework? Four? No?
Mine was just a lot of pages, and I think a lot of other people had several pages, like 20.
28 at first, I got it down to 16.
Yeah, and in most cases, what I was looking for is show me the first and show me the last.
Okay.
And because if you run your analysis several times, each time deleting a variable, you can give me that, but just make sure you make it very clear that the next 5 pages are only because I deleted one variable. You could also tell me in a sentence I deleted one variable and not include those 5 pages. So I think I mentioned, or as a matter of fact, I know I mentioned that including the first and the last is probably a reasonable way to go if you have to if you have to repeat your analysis a large number of times. Devitra?
I just had a question that by the time we look at the commonalities, we may have deleted a few variables already. And then we're looking at the commonalities, and this wasn't my data set, but we had a few that was less than 0.4. And we kind of deleted them all together, and then we just reran it, and then I was just kind of reading through, and they said to delete one by one. I mean, anyways, because we saw that one of them was like 0.2 or something, and the other was 0.4, and so do you, if you deleted it one by one, I mean, basically it's sort of readjusting again and again the variance explained. But is it okay to kind of delete at one shot?
I would. I get.
It was 0.4 and 0.2. So.
Yeah, I guess it depends on how. If they were, let's say you had 3 of them and they were all in the 0.2 area range, there's probably nothing you're going to do in your analysis that's going to get them up to a reasonable number. Although I still would. It just seems to me because it doesn't take any time. I still would. It's not a time thing, right? I would still delete the lowest one, run the analysis, and see. Okay, now what do I have? And it might be that one of the items jumps up some, but it yeah. And so that's just a best practice that I would follow if you wanted to delete all 3 of them because you're confident that these are never going to get high enough. There probably would be nothing wrong with that because we'd end up at the same place. You would get there just slightly sooner than I would and have a fewer pages of output than I would have.
And just one other thing was that, of course, we already are running this on things that are already at scale, but we had an interesting situation where we ran something and I think it was perfect. One of the items was like a 0.7 or so. And after we deleted the 2 of them together, that became like a 0.3 or something. And eventually that got deleted. But do you think in those kinds of situations where like when we first ran it, the item was explaining a certain amount of variance. So in my final thing, I would never delete that because I'm looking at the first time I ran it. I still delete the other ones, which are 0.2, 0.4, but do I just keep this one, which initially was good, and then sort of, does that question make sense?
I don't quite follow the workflow that you're. I think what really matters, again, because it's exploratory, is that you just can defend what you did, and it. I haven't seen much that's indefensible when it comes to exploratory factor analysis. People do a lot of different things. And so you probably would be okay But if you can show me an example, maybe on the break or some other time, I'd be happy to look at it. But I just don't quite follow exactly what you did. Good. So a lot of output. I'll look forward to that when I grade your homework this weekend. A lot of output. Anything else on homework 4? Let's this is about. I think we got to this point, and then we started rushing through these last, and I don't even think I covered the last couple of slides, but I think we spent a fair enough time on a reasonable amount of time on this slide, and we probably and the few of you that I talked to in our conversations here today, you were able to sort of make sense of interpreting the component, which is at the end of the day probably what you want to get to. You sort of want to get to this point so that you can have some understanding of how your data is structured. And remind me, how do we interpret that loading? So how do we interpret 0.733? What's the interpretation of that?
Is it the explaining variance?
Close, but not quite specific enough. It is related to explaining variance. Anybody else want to take a shot at how do we interpret the loadings?
That is above, isn't it 0.4?
There would be different criteria that we might use here, and this is a little bit. This isn't quite what I'm talking about in terms of interpretation, but it would be how we would determine whether our loading structure is appropriate, or do we have cross loaders?
So is it like how correlated those variables are with each other and not with other items?
Yeah, I think that's close. What it is, it's the correlation with that question with the component. And so in this case, the relationship between my first question, or that first question that's listed there, and that component, the relationship is 0.733. So it really is a correlation between the item and the component. What's the relationship between that item and that component? And what we want is items that are highly correlated with one component and relatively uncorrelated with the other components. And that's where we get into the criteria that we're going to use, that you might use to determine if your loading is appropriate or not. And so just as you're doing exploratory factor analysis, it's just useful to think about that as not just a number that you want to compare to, is it greater than 0.4? If it is, then it's fine, and as long as it's not greater than on any other component, it's also just fine. It's more than just that. It's actually a correlation coefficient that can just aid in the interpretation of your results. So does that make sense?
So when you have like one item that is loads on its own, like I have 3 components and I have one item load on its own, you expect the correlation to be really high, like that number?
If it could be, but it's not always necessarily really high.
What does it mean if it is?
What does it mean if it's a single item? It doesn't mean much. It's still a single item that probably just needs to be deleted. in most cases, most people would just delete that from the analysis.
Yeah.
Yeah, because it loads all by itself, and we're sort of adverse to single item scales because there's just a greater likelihood that there could. So so we're good with this, and let's just spend a few minutes here. So if you want to use your solution for subsequent analysis, you have to create surrogate variables that combine together the variables that load together from your analysis. So in this case, we would combine together, we would create some kind of surrogate variable that would use the first 4 questions as those 4 items would be one surrogate variable, and then the other variable would be the last 3 items. And so oftentimes and we've talked about this some in class, we can take an average of the items, which is a very common way. So just use SPSS, use transform, and calculate the average for each person for the items that load on each of your components is a reasonable way to do it. Some people may not create averages. They might decide to create just do a sum scale, and so it would instead of dividing by n, they would just sum the items, and they prefer to work that way. In my experience, it makes little, if any, difference. One thing that is useful, and we talked about this earlier in the semester, is realize that if you go through your data, so let's say these first 4 questions, they all do load on a single component. What happens? What should I do with the person who didn't give me an answer to the first question? For whatever reason, I have missing data. I have missing data for a person for the first question. And so how should I and if I'm going to calculate an average, how should I calculate that average? I no longer can calculate it. If I tell SPSS to calculate it using the mean function, it's going to give me missing. It's going to give me, if it's missing, if there's any missing data, if I use the mean function, if there's missing data, it's going to give me the mean for those that didn't have missing data, right? Yes.
Do you exclude cases that, what is it, case-wise or just-wise?
Yeah, I don't think I don't think we'd have an option when we do the compute, but it just, but you just have to be careful and make sure that if you have missing data and you're creating some scales or these surrogate variables, make sure that if you have missing data that you are managing that appropriately. And make sure that so for instance, if I use the mean function in SPSS, and if I am missing one of these response for one of these items from a person, what SPSS will do is it will calculate the mean for the other 3, and it will give me that number. Are you okay with that? As a researcher, are you okay with that? In some cases, we might be. What if they're missing all of them but one? Let's say you have 4 items in your that load on a single component, and one of your respondents answered only one of those 4 questions. Are you okay is it okay to calculate the average for that person for that one item, which that average would be just the score for that one item. I think there we're probably, it's getting a little bit clearer that I would be uncomfortable doing that. But there are ways to use SPSS in the transform function where if there's any missing data, it will leave it missing when you create the surrogate variable. And the way that you would do that, and I showed you this several weeks back, is instead of using the mean function in SPSS, you would just add up. You tell SPSS to sum the response for question 1, question 2, question 3, question 4, sum all of those up and put that in parentheses, and divide by, in this case, 4. And if there's any missing data, when you use that transformation, you will get missing data for the sum scale. Does that make any sense at all? Somebody help me out. Does that make some sense? Nobody's helping me.
It's making a mean score for the items that are present.
It's right, and it's making a mean score for the items that are present. And if there is any missing data, you just need to decide what are you going to do. And SPSS will do whatever you tell it to do. And I think you need to be thoughtful about how you do those calculations. Especially if you don't have much missing data, it's probably not going to be a problem. But if you have a fair amount of missing data, it's something that will always be a cause for pause and making sure that you're aggregating your data in a way that makes the most sense. In some cases, I don't know if I don't know of the examples we've talked about or the examples that I've seen. I don't know that anybody was using data that was measured on different scales, meaning some of your questions were measured maybe on a 1 to 4 scale, other questions were measured on a 1 to 7 scale, other questions maybe on a 1 to 9 scale. If you have that, obviously summing those together or taking the mean is going to be problematic because there's going to be different weight. If some of your questions were measured on a 1 to 4 scale, and some of your other questions were measured on a 1 to 9 scale, and you try to sum those all, you try to combine those all together, there's going to be different weight applied to those questions, and you're going to get a mean that is probably not what you want. And so when you do the factor analysis, it doesn't care how your items are measured. You can have some that are measured 1 to 4, and some that are measured 1 to 9, and some that are measured 1 to 7, and it can work with that and not, it won't cause any problems. But when you get to this stage, when you're creating these surrogate variables, if you have items that are measured on different scales, probably the best way to deal with that is just standardize all of the data. So it has mean 0, standard deviation 1, and then do a mean or a sum so that all of the items have the same weight in the final surrogate variable that you make. And of course, we're doing exploratory factor analysis, and we need to. It is exploratory. The way that the analysis is done is it just looks for and the methodology that we use, the procedure that we use is very much exploratory, and we need to be somewhat tentative about the claims that we're making, and just make sure that we are framing it as that this was an exploratory analysis, and subsequent work would need to be done to confirm your model. And we could do that with confirmatory factor analysis, or CFA, and that's a different approach altogether. It is not exploratory. It is very much hypothesis testing. You hypothesize a model that you think fits your data, and then you test whether that model actually fits your data. And we do that with a tool called structural equation modeling, which many of you have used or heard about for sure. And in one of the last 2 class periods, we'll take a little bit of time to talk about structural equation modeling and how confirmatory factor analysis fits within that larger framework. And so in most cases, what you'd also want to do, so you've done an exploratory factor analysis, you have several components that you're happy with, they seem to be theoretically meaningful, you're going to be somewhat tentative in how you think about those because it was exploratory, but we still would want to calculate our reliability. Cronbach's alpha is how we would do that. And in my case, for the analysis that I did, somebody give me what are cutoffs for Cronbach's alpha?
7.
Yeah, and so 0.7 is 0.7 good, or is 0.7 just the basement? Yeah, I'd say 0.7 is about the basement. You can maybe go a little bit lower than that. 0.85 is a good number. 0.9 is a good number. If it gets too high, I get a little nervous. If it's 0.99, it means, I don't know exactly what, it could mean different things, but it certainly could mean that people didn't discriminate much when they answered your questions, and they just circled the same answers all the way down. It may not always mean that, but it could mean that. So in my case, 0.64 and 0.57 clearly falls below a threshold that would be acceptable for most people. Maybe I could just try to publish it and don't mention what Cronbach's alpha is. Would that be acceptable? Huh? It doesn't seem like it, but as you read literature, you should read and look to see where not everybody reports Cronbach's alpha, right? Maybe they didn't run it. Maybe they didn't run it. I wonder why in some cases. But I can imagine running it, finding it to be substandard, and then, well, I'm going to use it anyway. I'm just not going to report it. That should feel shady, really shady. Right? Yeah, sketchy. It's not.
Shady.
Yeah, it is not. It just wouldn't be. It wouldn't be typical for sure. So in this case, I spent a lot of resources collecting this data, and this is sort of where I end up, and I need tenure. And so what do you do? And so I mean, it's sort of a unique. Well, it's unique, but not only that, it's sort of a precarious position. But I think most people would say that hopefully there's some data that you maybe couldn't use this, but maybe there would be something that you'd be able to salvage of this. Somebody remind me, when we talk about reliability, how do we define measurement reliability? What is measurement reliability?
You're consistently measuring the same thing. You're not measuring different things.
Yeah.
It's consistent over time.
Yeah, and so it's consistency, right? We think of measurement reliability and we think of consistency. How about measurement validity? What's that?
Measuring the theoretical construct you're studying, I guess.
Yeah. And so reliability is consistency, validity is you're measuring what you say you're measuring. So if I have a measure that I say is measuring romantic love, it should in fact be measuring romantic love if it's valid. What's the relationship between reliability and validity? There's a sort of a
Things can be reliably invalid. So if you have reliability, you don't necessarily have validity.
yeah, so reliability, good, very good. Reliability is a necessary but not sufficient condition for validity, right? Just because it's reliable doesn't mean that it's valid. If it's valid, is it reliable?
Yes.
It has to be. It has to be, by definition. If it's valid,
It's reliable.
it has to be reliable, right? And you think about those two definitions.
Targets.
Yeah, how can it measure what you say it's measuring and not do that consistently, right? It just so measurement reliability is a necessary but not sufficient condition for validity. And so in some ways, if I see a low reliability measure, what does that tell me about the validity? If I see a low reliability measure, what does that tell me about validity?
It's not valid.
Yeah, it's not valid. It's not a measure of validity, but your validity can't be any higher than your reliability. And so it just intuitively can't be. And of course, we assess reliability is a pretty straightforward, right? We can do convex alpha. We can do some kind of repeated measures, test retest to get reliability, and it's a pretty straightforward assessment where we get a number. Validity assessment is as much a logical argument that you make or a theoretical argument as it is a statistical argument. And so we test the two constructs using not only different techniques but sort of different logic. One is very straightforward. Here's a number. The other would be a narrative kind of description with some statistics potentially thrown in there. So in my case, we're not reliable, therefore our validity is also subject to all kinds of concerns. And then the rest of what I have here is just some descriptive statistics that I ran. Given what I found about my reliability, it probably doesn't warrant doing a whole lot here because they're not reliable. I really have to go back to the drawing board and figure out what other kinds of questions can I ask that would allow me to increase my reliability. What would be one way that you could increase your reliability? Just very straightforward way. Yeah, just add more items. Add more good items, hopefully. The way that the formula works, adding additional items, all else being equal, will almost always increase your measurement reliability. It's just the way that it works. Add more good items, and there's no doubt that your reliability will increase. And so that would be the strategy that one would want to employ there.
Did you also just delete bad items? Like there was one item on there that would increase it to 0.6.
Yeah. So in this case here,
It doesn't really get much better.
yeah, and
It gets
so
worse.
in this case, when you run convex alpha in SPSS, one of the preferences, it's not a preference, it's not a statistic.
Scale if item deleted.
Yeah, and I don't remember where it's at, but I think there's only like one dialog box. Or
Yeah.
if there's two, click both of them and find the dialog that says scale. If item deleted and put a check mark by that one, it's always useful. And in this case, we could delete the fourth one, and we go up a little bit in terms of no.
We go
It
down.
goes
We
down,
go down.
that goes to that top one, that one.
And here we
Go down to.
go down as well. Yeah, and so in some cases if we delete the fourth one, we go from 0.638 to 0.61. Here, if we delete, we go from 0.57 to 0.54. If we had more items, and let's say we have 10 items here, oftentimes you can find if you have 10 items or 8 items or 12 items, that if you delete one of those items, it can make an improvement on your reliability. With so few items, just the way the formula works, there just is not a lot to be gained there by deleting items. So does this make sense? Questions? Should they turn the heat on or off? Is it hot in here?
It was much worse yesterday.
Was it?
Much worse.
Oh, yesterday.
Yesterday it was an armpit.
But I was in the
The whole
library and
upstairs
the like
smelled
furnace
like
was actually on.
bodies.
Thanks.
But usually it's really cold in this building, right? It's like,
I'm sure.
huh? So the air conditioner,
There's
It's just never ideal.
it's never ideal.
I think the PCC has moved some items so they don't have to run the AC constantly, like to preserve documents,
yeah.
which is one of the reasons why this building is always freezing. So I think that's part of the reason.
Huh. Dang PCC. So let's look at assignment 5. Pretty straightforward, but you can be thinking about the data. And this is going to be due, what did I say? It's the 5, it's April 5th. So April 5th, you can change the due date on your notes if you want to, but you're going to use SPSS to perform a two-way ANOVA, not a one-way ANOVA, not a three-way ANOVA, with theoretically, no close quotes, just theoretically open quote, meaningful variables, and so I think the data that all of you are working with, I would call it theoretically meaningful. And what we don't want to do is just sort of haphazard. We have to have some logic that helps us. And then we want to examine, and we're going to get to this as we start talking about interactions. We want to examine the simple effects, regardless of whether your interaction is significant or not. In most cases, in many cases, the interactions won't be significant just because that's the way it works out. But even if it's not significant, we want to sort of take those steps as if it were significant, because taking those steps can be instructive, and it will be the only opportunity that we'll have with this homework to sort of work through those steps. So we want to examine the simple effects, and again, let's relate it to interactions, and we'll get there. And then we want to annotate your SPSS output, write a paragraph that reports results, and then include a table of cell and marginal data, and we'll talk about that, and an interaction figure, again, regardless of whether your interaction is significant or not, okay? Make sense? So you can take a break from that in terms of not having to get that done next week. One of the things, and we'll get to this towards the end of this set of slides, and I count, or my computers tell me there's 55 slides in this particular deck. So we have at least a couple good days of lecture material here. But towards the end, we're going to get to a point where we talk about what should I use? Should I use regression or should I use ANOVA? And it's not always clear cut, but in some cases it's more clear cut than others. And so we'll talk about just sort of have in your back of your mind. We'll talk about that as we get to that point.
So I know people who use it, obviously I'm like learning as we're going, but I know we talk about like harking, which is hypothesizing after you, so you said like choose, that's like changing your hypothesis to match something that you found. But like just now you said you have to decide whether to use ANOVA or regret, so you can't do both of them and then just see if one of them. So you're not changing your hypothesis; you're just going through other statistical tests.
Yeah, I would feel doing the same analysis with ANOVA and with regression will get you exactly the same results.
Oh, okay.
It's just that in some cases it's more straightforward to do ANOVA. In other cases, it might be a bit more straightforward to use regression. And it in some cases, either one of them would be. But if you do exactly the same, if you do an ANOVA, that's a two-way ANOVA, you'll get exactly the same results if you replicate that ANOVA with multiple regression. It would take a little bit of work to do that, but you would be able to do that. And we'll talk about that work as we get into this some more. So just to have that in the back of your mind as well, it really is it's an important question that a researcher will answer, and as they do their analysis, as they collect data and they determine how they want to analyze their data. So analysis of variance is used to test differences among more than two groups. So if we have just two groups, experimental condition, control condition, for example, what's the appropriate test for that? It would be a t-test. But if we have three groups, experimental condition 1, experimental condition 2, control condition, we have three groups, ANOVA would be a better choice than doing the t-test. I'm getting a little bit ahead of myself. And so with ANOVA, we have generally more than two groups. There would be some exceptions to that, especially when we start talking about two-way ANOVA. With a one-way ANOVA, we have a single independent variable. So the one-way means one independent variable, two-way means two independent variable, three-way means three independent variable. I've never seen people do more than three-way ANOVA because we certainly don't have theory that helps us interpret four-way interactions. And there's just no theory we don't have theory that really helps us understand three-way interactions for the most part. There might be a few exceptions. I haven't seen or am I aware of any. And so three-way interaction would be probably so three independent variables would probably be as far as you go. There might be would be very few exceptions to that. I've seen some exceptions to it, and it just seems like they really are just it seems like they probably were running a bunch of analyses, and the four-way with four independent variables, it seemed like that was the one that had the results that they found to be most useful, and so they therefore made the argument for doing a four-way ANOVA. But those are rare and probably ill-advised. So it might seem reasonable to use multiple t-tests if you wanted to compare a variable with more than two groups, right? So if we had experimental condition 1, experimental condition 2, and control condition, we could do we could do a t-test between experimental condition 1 and experimental condition 2, right? We could do another t-test between experimental condition 1 and control, and another t-test between experimental 2 and control, right? We could do three different t-tests, and we could discover all. We could discover all possible. We could look at all possible combinations, and we could see if there's any significant difference. That might seem reasonable. However, performing those multiple tests to compare groups changes your probability of making a type 1 error. And the question is how much does it change the probability? And to answer that question, and this is just a good topic to have working understanding of. The formulas are pretty straightforward, and you probably wouldn't even need the formulas in most cases. You'd be able to do the calculations on your own. So if we want to answer this question, how much would doing those multiple t-tests change my probability of making a type 1 error? We first have to answer the question, how many possible comparisons will you be making? And to answer that, we take k times k minus 1 divided by 2. And so let's say we have 3 groups. It'd be 3 times 2 divided by 2 is 3, right? And so if we have 3 groups, we can compare group 1 with group 2, group 1 with group 3, and group 2 with group 3. That's it, right? It's 3. If we have 5 groups, it's 5 times 4 divided by 2, and we'd have 10 comparisons, right? And so you'd be able to, if you had a board, you could, isn't it? Yeah. Thank you. You were shaking your head.
No, I wasn't following your head.
You could write out your groups, and you could draw arrows, and I've done that before. How many comparisons do I have here? And you could draw those all out, and but this is a much easier way to do that. And so, how many comparisons are you going to make? And then how much does it inflate your type 1 error rate is equal to 1 minus the quantity 1 minus alpha, whatever you set alpha at, 0.05 in most cases, raised to the c power, where c is the number of comparisons being made, the number that you get from up here. When we do, and we'll look at an example of this here in a minute, when we do group comparisons with ANOVA, we can make some adjustments so that we don't inflate type 1 error. You could make those same adjustments if you did t-tests, but there would be an extra step or 2 that would be required, and it would just make more sense to do it with ANOVA than doing it with multiple t-tests and then making that adjustment on the back end. So just an example, here we have 5 groups. Of course, 5 times 4 divided by 2 is 10. And so if I did a study where I had 5 groups, I'd have to do 10 different t-tests. And I could report all of those t-tests in a nice fancy table and show which ones of those are less than 0.05. But my actual probability of making a type 1 error is nowhere near 0.05. It's actually closer to you almost have a 40%, or you have over a 40% chance of making a type 1 error, given the number of comparisons that you did all at alpha equals 0.05. So these are useful calculations to have, in the back of your head, and so useful, I think, that you should put a note in your notes that you should know this for the exam. I may not put it on the exam, but it wouldn't surprise me if I put a problem on the exam. Your friend says I should do, or maybe it'll be a take-home exam too. Your friend says they're going to do 6 t-tests, or do 16 t-tests, or they have 6 groups, and they're going to do t-tests for all of those. Persuade them not to do that by showing how much it will inflate your type 1 error. And I would look for you to give me some evidence that would use these couple formulas here. Does it make sense? So good stopping place. Let's take a 15-minute break. Hopefully it cools down if you open the door.
Recording.
I